Differentiation for merit. Question 1c, we're going to use differentiation of parametric equations, and so we come down to dx dt and dy dt. Just getting these two bits correct here is equivalent to getting a achieved question. And so, as with all the merit questions, there's a stage where we get achieved, and then we complete the question, we get a merit. And so I get dy dx equals -2 sine 2t over 2 cos t. Now, to get to our answer, we have to use some trigonometry, and we've got this double angle formula off our formula sheet. Sine 2a equals 2 sine a cos a. Or in this context, sine 2t is 2 sine t cos t. And for part D, we're looking for a gradient of a tangent. So differentiate y equals, and if its gradient's parallel to the x-axis, then the gradient equals 0. Now, I've seen people approach this sort of differentiation in different ways. I would bring the denominator up as a power of -1, but I've also seen others use the quotient rule. Now, it doesn't matter, we will get to the same answer. So, by my method, I bring the bracket up to the power of -1, and I've expanded that bracket. So, 2x minus 2 to the power of -1 comes e to the -2x plus 2. And when I differentiate that one, I get 4e to the -2x plus 2 times -2 and plus 8, or -8e to the -2x plus 2 plus 8. So, putting my derivative equal to 0, I need to solve. So I bring the -8e to the 2x plus 2 across to the left-hand side, dividing each side by 8, and it's e to the -2x plus 2 equals 1. Remember, anything to the power of 0 equals 1, so e to the 0 equals 1, leaving the power -2x plus 2 equal to 0. Solving, x equals 1. The function is not differentiable where it's not continuous, or there's a break in it. So these two are obvious places where it's not differentiable, because we can see the asymptote and we can see the step there, but it's also not differentiable at this point on the curve where x equals -1. The second derivative is less than 0 for that whole section of the curve that I've highlighted in blue. And so from this point here on the left hand side of the curve, the gradient at present is a very high positive value. And the gradient steadily decreases to the maximum point where it is 0. And further across to the right, it's still decreasing because it's becoming a larger and larger negative value. So the whole section of that blue curve has a decreasing gradient, or second derivative less than 0. The only place where the function is not defined is at this value of x equals -2, where you have a asymptote, and on one side the curve is going to -infinity, on the other side it's going to positive infinity. At x equals -1 and x equals 2, it does have a defined value, and that's shown by these two black points here. And so, following on from part 3, the value of the function where x equals 2 is at this value of the black point, y equals 4. But the limit where x equals -1 is not the black point on the x-axis, but actually this hollow point here, because this is the value of the curve as you approach from the left or the right. As I approach x equals -1, the curve is approaching this hollow circle at y equals 3. Minimum hourly cost means I need to differentiate my equation c equals and put that gradient equal to 0. Now, to differentiate c equals 4v plus 1 million over v, don't try to differentiate that domain given on the right hand side there, that are underlined in red. That's just giving you the range of values that we can use for v. It's not part of the function you're going to differentiate. So I'm differentiating c equals 4v plus 1 million v to the negative 1, which becomes 4 minus 1 million v to the negative 2. So my gradient equation equals 0, and to solve that I'll bring the 1 million over, whoops, I see I've made a mistake. So my gradient equation is 0 equals 4 minus 1 million over v squared, and when I solve that I'll bring the 1 million over v squared across to the right hand side. Cross multiply, 1 million equals 4v squared, dividing by 4, and then square root. V equals 500 kilometers per hour. Now the value of v is not the answer to the question. We're asked for the minimum cost. So I substitute v back into the original equation and come up with a minimum cost of $4,000. Question 3c. A function's increasing when the gradient is positive, and so I'm going to differentiate and find where the value of f dash x is greater than 0. And when I differentiate fx, notice that this bit on the right hand side is a product rule. So differentiate write down the first, differentiate the second, plus write down the second, differentiate the first. So after differentiating, multiplying, collecting like terms, I should end up with a gradient equation of 4 minus log x. Now this is the piece that I want to be greater than 0. Now the inequality signs tend to jump around a bit depending on how you want to write this. I've changed signs and changed the inequality sign at the same time here. May not be a good idea. I've got log x now as less than 4. Log x can be rewritten as e to the power of 4. Now that's going to be greater than x. The e comes across to the right hand side, and you get e to the power of 4 bigger than x. And when I solve that, I end up with x less than 54.6. So just have to think a little bit about how those inequality signs work. The other thing to watch for in this question is that's not the end of the answer, because log x is undefined for less x than or equal to 0. If you try anything negative on your calculator for log x, you'll get math error. And so we have to include x greater than or equal to 0, less than 54.6. Question 3d, we're trying to put these three bits together. There's a change in h at a constant rate of 1.5. We need to find the angle of elevation, and I've got my triangle over here. So I start by writing what I'm given, dh dt equals 1.5, and what I require, d theta dt. And those two are linked by the chain rule, d theta dt equals dh dt times d theta dh. The d theta dh comes from the triangle. Firstly, tan is opposite over adjacent, so tan theta is h over 20. When I cross multiply, h equals 20 tan theta, differentiating dh d theta, 20 secant squared theta, so I'll use the reciprocal in my answer because I need d theta dh. And so I've substituted into that chain rule, and d theta dt equals 1.5 times 1 over 20 secant squared. I need the value of theta to substitute into this, so I'm going to go back to my first step, and I've got this piece in the question where p to q is 20 and p to the observation point is also 20. So h equals 20, tan theta 20 over 20, which comes down to give theta equals pi over 4. To evaluate secant squared pi over 4, remember secant squared is 1 over cos squared. So it's 1 over cos pi over 4, and that value squared. Secant squared equals 2. So we finish the question off, d theta dt equals 1.5 times 1 over 40, or 0.0375 radians per second.